Welcome back to the series of lectures on high-performance scientific computing. Today we will look a little bit further into the codes that we were discussing, which we were parallelizing using OpenMP. In the previous lecture, we saw the parallelization of the problem of the steady-state heat conduction, which was described using the Laplace's equation. We discretized this problem on a square grid, which was regularly spaced with even spacing of delta x and delta y. The number of nodes in the x direction and the y direction were the same. We had described what the discretized equation was for this partial differential equation, and then we had chosen the successive over relaxation method to solve this efficiently. The first thing now we will do is to do a detailed time study of the same code. So for that, we'll go back to the terminal, and just to remind you, I will now open up the code that we had written. So this is the code that we had written for a parallel implementation of the Laplace's equation using the successive over relaxation technique. And we had essentially parallelized this code using the hash pragma OMP parallel for statements. We had seen how the effect of not mentioning the indices to be private resulted in an incorrect calculation. This correct implementation now gives us the exact answer every single time, or what is known as the code reproducibility. Whether you run the code in the serial mode, parallel, with different number of threads, the answer that you will get is always the same, as it should be. Now let us do a reasonable time study. I will recompile this code just for safety's sake, just to ensure that I did not make any mistakes while creating the executable. And I will give the target to be Laplace. So in the first case, what we will do is we will just get the serial timing. So we will say OMP num threads is equal to 1. Now this is one way of doing a serial code where we just say that there is one thread, and when we time the code, we get a time of about 3.21 seconds. Now, let us report this time. Now, ideally, we had spoken that we would take an average of several times. But what we can see is that every time that we run this code, we get a slightly different time, approximately equal to 3.21. So just for convenience sake, at this moment, we will not be taking an average of multiple runs, but ideally you should be taking at least 5 runs to average the time and report it. So now I will go ahead and I've created a spreadsheet where I said where I used one core. I can also call it cores/threads, and with one core the time that I get is 3.21 seconds. Now, if I rationalize the speed up, this is going to, now I'm just going to put up a formula over here. I'm going to say the time that is obtained over here is B3 divided by $B $3. So in this case, it should come out to 1. Now let us find for 2, 3, and 4 cores or 4 threads, what is the time that comes about. We go back to this, we change the environment variable to 2, and then we run the code again. In this case, we get 1.704 seconds. So I'm going to go back to my spreadsheet and put down the number 1.704 And I will now copy this formula over here. I have actually made a mistake in the formula. It should be the other way around. In this case, there was no issue because it was the same number. Here, we will get the correct speed up. So we get a speed up of 1.88 for 2 cores. Now let us change it to 3 cores. The time that we get is 1.227. Let's go and report this over here. And when I copy the speed up formula, I get a speed up of 2.6. Let's now go to 4 threads. And now let us execute the code again. And in this case, you get a much lower time of 1.04 seconds. Let's go and report this back onto this sheet. You can see now the speed up is increasing, but at a slower rate. Let's see what happens if we increase it to 6 and 8 cores. We get a slightly higher time. With 6, we get 1.08, which is a worse off speed off than 4. And then let us try one more with 8 threads. And we get a time of 0.97. And let's see what is the speed up that we get. So now you can see as we are approaching the limit of 4 threads, we are starting to sort of asymptote to the speed up that we are getting. So for 6 threads, it went to 2.97, the speed up, which actually was slower than 4. But then for 8, it just improved slightly at 3.33. Now, this is due to the vagaries of the hardware architecture and the OS scheduling. This particular machine has 4 cores, and hence this is sort of the ideal sweet spot where you want to run the machine. As I mentioned earlier, ideally we would like to average these times over several runs, typically about 5 runs, and then compute this speed up. Now, if we were to plot this speed up, you will see that the nature of this graph would be that it is asymptoting to some value around 3. That's because of the nature of the machine that we are running on. If we had a computer which had many more processing cores, like a server, it's quite possible that we would get to see some more speed up. But again, we must remind ourselves that this is a fairly small problem and the maximum speed up that we can achieve is probably quite low. Let us also now look at the effect of the placement of these directives. Now, if I go back to the code, so this is where I have parallelized the code. Now, I can change the program definition slightly over here by parallelizing the inner loop rather than the outer loop. So I can first take this code over here and put the directive over here. And in this case, I will say, let's say it is a private I, j. Similarly, I will take this code over here and put it over here and just parallelize the innermost loops. Let's see what is the effect of this. We would need to recompile the code at this point of time, since the program definition has changed. Now, remember our environment variable is still set at 8. We will now change it back to 4. And let's see what is the effect of this code. you can clearly see that we have an issue right away. The reason is how we have declared the variables inside. So if I go back to the program definition, I see that I have had a private I and a private j, but in reality it should be just a private j. And in this case as well. Now let us recompile the code and run it. And now you see the code is running with 4 threads. But what is immediately noticeable is the fact that the code is very, very slow. We'll wait for the program to get completed. Now the program is complete. You can see the program definition is correct because we are getting the correct answer. If you remember from the previous lecture that if the last 4 digits of this last output was 7671, we were getting the correct reproducible output. But the time taken now is significantly higher. It is about 33 seconds. So let us go and just report it back in the Excel sheet that we have. So we'll say this is a new time, and we'll call this a new speed up. And here the new time right now for 4 cores is 33.67. We haven't computed what the serial time is going to be, so let us now compute what the serial time is by saying that we're just going to have 1 thread, and then we say Laplace. In this case, you see you're not slowing down the code much. You're getting to about 5.1 seconds. We can run it once more to see what's going on over here. So it's about 5.05 or 5.06 seconds. So we can note the new time to be 5.06 seconds. And we can now again write the formula for speed up. We can say that this is d3 divided by, or rather d3 divided by d3. Oh, I'm sorry. d3 divided by d3. Yeah, we get a speed up of 1. Now, if I copy paste the solution over here, I get a terrible speed up. In fact, I get a slowdown. My serial code is actually running faster than the parallel code. So we must analyze why we have gotten such a worse off result. The answer lies is in how we have parallelized this code. So if you go back and look at the code, you will see that by parallelizing the innermost loop with a parallel for, what happens is that for every iteration of I, there will be threads that will be created, which will then do the parallelization of the J loop, and then the threads will get destroyed at the end of the J loop. Now this is going to happen about 1,000 times per iteration over here and another 1,000 times over here per iteration. Whereas in the previous implementation where we had the OpenMP parallel for, above this for the outermost loop, for every iteration parallel threads would be created once and destroyed once over here, would be created once over here and then destroyed once over here. So the overhead of creating threads thousands of times is significant. So there's a lot of management that needs to be done to create threads, allocate memory for these threads, and then destroy these threads at the end of the loop. Hence, it is always better to parallelize the code on the outermost loops And please do remember that in this case, you have to make the index I also private. Now, if I go ahead and recompile the same code and I run it with 4 threads, I should get a reasonable answer. We get back to the original code with roughly the original timing. So this was an example of how placement of the OpenMP directives can have a significant effect on the performance of the code. So one needs to be very careful of where you're placing the OpenMP directives. We shall now look at one more example which involves a reduction. So the next problem that we will look at is the trapezoidal rule for numerical integration. The trapezoidal rule approximates an integral by dividing the area under the curve into trapezoids. This is typically the formula of the integral where you sum the approximation by taking the interval to be defined as b minus a divided by the total number of divisions that you would like, and h is the interval length. And at every h by 2, you are going to evaluate f of xi and f of xi plus 1 and then make the summation. So this is going to basically compute the sum of the trapezoids, and this will end up completing the numerical integration. We will now integrate a function f of x square within the limits 0 and 1, and we'll see first the serial implementation of this code. So this is the serial implementation of the code, where now we have defined the number of intervals to be 1000. We have defined the function f, which returns the value x square, which is essentially the function to integrate. X square can be replaced by whatever function you would like to integrate. We are now setting the integration limits a and b over here. We want to integrate the function x square between the limits 0 and 1. We are defining the step size to be the interval length divided by the total number of intervals that we want. And we are going to initialize the value of the integral to be 0 initially. The serial version of the code is now basically going to loop through all the n sample points, compute the two limits of that particular small interval, x1 and x2, evaluate the function at the points x1 and x2, and then multiply it by h by 2, which is essentially the trapezoidal rule. So essentially what you're doing is you're taking the average of the function between those two limits of the interval and then multiplying it by the step size h, which will give you the area of that small strip. Now you add up all the strips together, you get the value of the integral. So let us now first verify the answer correctly by running the serial code. We will compile it using this. And when we run the code, we get an answer that the estimated integral is 0.33. So if you were to integrate the function f of x square in the interval 0 to 1, the analytical integral of f of x square is x cube by 3, and within the limits of the integral it is 1 by 3, which is 0.33. Now let us try to parallelize this code. So the first thing that I will do is find out which is the for loop I need to parallelize, and which is in this case only this one for loop. So what I'm going to do over here is I'm now going to say hash pragma OMP parallel for, and because we know that we are going to get a private value for I, we are going to say private I. Let us now compile this code and see what the result is. So immediately we get an error saying that you cannot use the the private eye. The reason is, if you look back at this code, we are now saying declaring the integer over here. So when you say the index is being declared in the for loop statement over here, it automatically implies that for each thread you're going to get a private eye. So let's remove this. And let's now recompile it. Now we have successfully compiled the code. Now let us try to execute this code and see what answer we get. We get 0.30, which is a different answer from 0.33, which means that we are not getting our code reproducibility. Let us rerun this code, and we're getting a different answer again. So not only we're getting the wrong answer, we are not able to get the wrong answer reproducibly. So, which is a big problem for us. So we're going to get random answers every time that we run this code. So where are we going wrong? So let's go back and revisit the code. So if you look at the code over here, we are now going to see that there are a few, the reduction of this entire loop is being done in this global variable integral. Integral is being shared by all the threads. So we have to ensure that when the sum is being done into this integral, it is being done in such a way that data race conditions don't exist. The easiest way to implement this is that because this is a reduction problem, I will add the reduction data clause. So I'll say reduction, and the operator that the reduction is going to do is plus, and the variable that I'm going to do is integral. So now I have specified that I'm going to do a summation reduction for the variable integral, and this is now going to ensure that each of the threads has parallel private copies of the variable integral, and then a global sum is computed. Let's go back and compile this code. Now let us run this code. Now we're getting the correct answer with a reasonable amount of error. So we're getting the same reproducible answer with 0.33. So this gives us confidence on using the reduction clause. We can do a very similar timing study as we did for the steady state heat conduction problem with the trapezoidal problem. I will leave that as a homework to the class. Let us now go on to the next problem. So we looked at the trapezoidal rule for numerical integration. We can now look at Monte Carlo integration as well. Now, what is Monte Carlo integration? Here we are using some random sampling to approximate an integral. So where we take some n random samples in the domain, we generate n random points, compute the function values at each point, and then find out what the average value is. When we look at the average value, that estimates the integral if you're looking in the domain 0 to 1. Now, the advantage of this is that it works very well for high dimensional problems. It can handle irregular regions. The disadvantage is that it has slower convergence than deterministic methods, in the sense that it being a random sampling, you are now going to get different answers. So you'll have to set what is the tolerance that is acceptable to you, because how much of a variation is acceptable to you in the least significant digits. That's something which you'll have to decide. So if you want an answer which is more accurate, that means you'll have to take more and more samples. And obviously, if you take an infinite number of samples, which is theoretically not possible, you will get the correct analytical solution. But a large number of samples will get you close to it. So now let us go back and look at the code for the Monte Carlo simulation. So here is the code for Monte Carlo simulation. What we are defining is we are taking a million points over here. I am again computing the function, and in this case the function that we need to integrate is x square. We are now saying that we have the sum over here instead of the variable integral. We have the index I outside now, declared outside. So what the serial code looks like is that you loop over some n random points, you assign a random value of x to this point in the range 0 to 1, and then you compute the sum. And finally, the integral is nothing but the average of the sum. The function srand seeds the random number generator with a unique seed every time the program is run, so that you get sufficiently large random numbers. Let us execute this code in serial. And when you execute the Monte Carlo, you see you get an answer which is approximately equal to what we were getting using the trapezoidal rule. Let's rerun it again. So here, with about 1 million sampling points, we get it with the accuracy up to 2 decimal places. From the 3rd decimal place onwards, we are getting some slightly different answers. Now let us parallelize this very quickly. So here we will now say hash pragma OMP parallel for, we must remember to say private I, private X, and we must also say reduction of plus sum. Okay. So once we do this, we can now compile the code with the FOpenMP flag. And now run this code to get the same answer. If we increase the number of samples, we are going to get more accuracy. So far we have seen 3 different codes. 1, the implementation of the Laplace's equation. 2, integration using the numerical technique trapezoidal rule, and numerical integration using random numbers using the Monte Carlo technique. Thank you.